Okay, let's start with a question. Actually, you don't need to answer it, but who loves sending audio messages? I personally hate receiving them. Fortunately, Telegram offers a very good feature at some price, transcribing your audio messages into text. Let's check how it works for Armenian language. Okay, even if you don't speak Armenian, you can see how it doesn't work. So it's completely unusable. My name is Alexan, this is Ara. Today we are going to present you our journey on creating a fully open source Armenian ISR model, the model that actually is able to transcribe the audio into text. Okay, since we have very diverse auditory here, we'll try to keep things as non-technical as possible. Though we're happy to answer your very deep questions at Q&A. Also, you can visit our repository and read our paper for full technicality. Okay, so as I said, ISR, automatic speech recognition, is a technology that stands behind transcribing from text to audio. As any ML model, it requires some specific type of data. So for this ISR data, we need actually pairs of audio and the precise transcription in text, what that audio presents. Before Nvidia started working on this, we had only 12 available hours of Armenian data, 5 at MCV, Mozilla Common Voice, and 7 hours at Floors. Floors is Google's dataset. Both, like, I'm talking about the fully open source data now. We applied 4 techniques: offline and online crowdsourcing. We used open source audiobooks and also pseudo-labeling technique. With that, we were able to reach from this 12 hours to nearly 300 hours. Half of which is labeled data and half of which is unlabeled data. So we'll speak about the difference a bit later. Also, we were able to achieve 9.9% word error rate. Just to give a bit of intuition what word error rate is, it's literally what it says. It's how good or how bad, in this case, model gets the words compared to the original text. And also, another our contribution is we did not only open source the model, we also open sourced the dataset and, which is most important, the full pipeline. Because we'll speak about it a bit later, but one of our focuses here was to use Armenian language as a case study and make it like one button click available for any low resource language to reproduce results. Okay, so speaking about the timeline, it took something like 4 months of engineering work, and from starting of our journey to the end to the open sourcing the model, it took 11 months. So we'll go on each step, on each step by step. Okay. First thing what we did is we collaborated with 2 Armenian major universities, AUA and USU, Yerevan State University, with data collection events. I'm not sure if you have heard of them, or maybe some of you have participated there. So as I said, in MCV, Mozilla Common Voice, it's a platform developed by Mozilla. It's fully open source, and its main target is collecting text and speech data for training this type of models. So the Mozilla Common Voice dataset for Armenian language had initially 5 hours, of which 3 hours were validated. With our offline events, where we gave merchandise and certificates to participants, we were able to expand this amount of data to 48 hours total and 24 hours of human validated data. Just a bit numbers in terms of money. What we spent something like $1,000 to produce all the merchandise and all the certificates, so it was just part of prices. Another important thing that this MCV did, it raised awareness and community engagement. So we tried to speak about the problem that Armenian language don't have enough dataset available online. The next step was taking the offline crowdsourcing to online crowdsourcing. We cooperated with an open source Armenian magazine. We took their articles, extracted the sentences out of these articles, developed a 3-stage pipeline, and used online crowdsourcing platform to generate data for us. So this platform was literally, we're making tasks and asking the platform users to vocalize them. So just to read out these tasks. Okay, so just a bit deeper inside the pipeline, how it worked. As I said, it was three-stage pipeline. In the first stage, we took all the articles we received from the open dataset. We filtered out the sentences that we don't need. So we dropped, for example, non-Armenian sentences that don't fully consist of Armenian language, or very long sentences or very short sentences, and uploaded them as the tasks to the platform. The next part is basically the most interesting part here is how we validated it. So the platform itself provided us, and it's very universal, so we can apply it to any like crowdsourcing platform. It provides us hard tools to filter out the users that we don't like. So for example, one of the tools was if in a very short time the user completes a huge amount of tasks, we probably think that it does not do what we really want. So either it reads the text too fast or it doesn't even read the text. And with manual validation, we came across to such people that were just generating some random noise, and it had nothing to do with our task. So these were hard filters that we provided. Even though we had them, the still data we used was not we collected was not ideal. So we implemented the second step. We had dataset collected already from the Mozilla Common Voice event, so we had like 50 hours. We trained an in-house ISR model, and we, by empirical experiments, we came to some threshold. So we didn't have like the ideal model, but we had some model that somehow represents Armenian language, and we just came with a big number, and we had a filter. If the audio doesn't correspond to the text we asked with even greater than this value, then we throw it away. And we reject it, and then we re-upload the data. So in total, we did something like 3 iterations of this. And the final stage was about downloading the results and post-processing to get to the stage of training ready. Okay, so these were these 3 3 steps of the pipeline. Now I'm passing the microphone to Ara.
Okay, let's continue with the other data source type that we used, it's audiobooks. And let me actually remind you, one of the key notes of this presentation is to do the case study on Armenian, but the overall goal for this project is to illustrate that for low resource languages, maybe it can be Armenian, I don't know, maybe Georgian, or any language that has few hours of data. We can use the pipeline, this pipeline, to increase the amount of data and develop good models. A common thing for various languages is to have audiobooks. So another approach for us to go is to explore the audiobooks themselves because it's scalable to other languages. For Armenian, we have this Gurkaser, which is a library that has many novels, fairy tales, folk tales, and the beauty of this kind of data is it's a very diverse in terms of various intonations, in various prosody styles that you have in the audiobooks, because authors often alter their voice during the speech, the different intonations within these fairy tales or dialogues. So it's a very good source of audio. But there is one problem. The major problem is that majority of these audiobooks are very long. By saying very long, you can have multiple tens of minutes or even hours long audios for a single book. Thus, the pairs that we want to use in our ASR that are actually a couple of seconds long audios. In this case, it won't work because we have for each book, let's say 40 minutes long audios with the corresponding transcript. And it's very difficult to process with this data because when you load the data, usually how the computer reads the audio, it's a whole bunch of vectors, and just don't want to go into the deep details, but it's memory consuming, it's not fast, it's not, for deep learning models, it's difficult to capture all these dependencies when you have very large data, let's say data points. So we needed to find a way to split the audiobooks and get a suitable ASR suitable data format out of these long audios. And here's, don't get distracted, it's actually moderately easy to understand without going into the depth into the details. Let's see. In the first stage, we have this MCV dataset, this Mozilla Common Voice. Oh, sorry. We have this Mozilla Common Voice dataset, which we used to pre-train, to get a baseline model So as MCV dataset was kind of restricted, not that much audio available, the model, this baseline model itself is not a fantastic one, but we'll use it in later on. I will talk about that. In this section, you can see this is the audiobook and the corresponding transcript. These two are long enough. So we pass these audiobooks into the VAD, or it's called voice activity detection. It's just an algorithm that detects, given the audio, where are the speech segments and where are the silences. So you can split the audio in the silences. With this approach, we managed to obtain from long audio various small chunked audios, like 2 to 3 seconds long, which are too short, and we will address this later on. Okay, we obtain these small chunks, and what we do next, we don't have the corresponding text for these small chunks. We just use this baseline model, as we said, to infer or to predict the texts in these small chunks, which are, of course, not guaranteed to be true. But we do this inference and obtain the corresponding predicted texts for these chunks. Then what we do, this is a much more technical part, like how do we do this text matching. And essentially, we have a long transcript, you can imagine, and very small predicted transcripts. And we go with a sliding window over this long transcript and try to match with these predicted ones using character error rate. It's an alternative to word error rate. We need a more precise way to match the texts. It's a both dynamic and greedy algorithm, but we won't go into the details. But this algorithm helps to match match this text and from the original long transcript to obtain the corresponding correct ones for this. And eventually we obtain all the labels or the text for these small chunks. And then we need to merge it. By saying merge, you have a couple of very short audios. We need to enlarge it a bit to get 50 seconds long audios. And eventually to get up to, let's say, 50 seconds audios. And this is already a supervised data set, which we can use further on. And this approach can be extended to many languages. Just the side note is that we need to have at least a small amount of data to get an appropriate ASR model. And by saying appropriate, we need around 30% word error rate, which is mostly easy to obtain. Okay, so another huge and available data set that we could use is YouTube, of course. So there are a lot of audios in YouTube, even in Armenian. And we use a tool to scrape the data from YouTube. But again, this problem is that there are long hours of audios. Here we'll use another approach. First of all, we will cut it using the same WAD to get shorter chunks. And we use this thing called NumFOCUS aligner. It's like alignment between the text and audio. It says within the audio which part of text was spoken during which timestamp. And by doing that, we can, by extracting this data, we can split the audios to get the 20-second long chunks. But the problem is that we don't have transcripts again. And the tactic to obtain these transcripts is pseudo-labeling in our case. As Alexan was talking about the unsupervised data that we obtained, this is the one. So again, some fancy pipeline, but eventually what we do, we have these YouTube long audios. As I said, we use this NumFOCUS aligner and voice activity detection, get up to 20 seconds long audios, but we don't have the corresponding texts. Let's keep this in mind and continue from there. We have this MCV and Fluor's open source available data set. We use this to train an Armenian baseline ASR model. So we use already trained English model, fine-tuned on this Armenian data, and obtain an Armenian ASR model. Then we use this Armenian ASR model to predict this corresponding texts, a similar pipeline that we did last time. But the interesting thing is that this is an iterative algorithm in the sense that after predicting these transcripts, we then use it to retrain the model. So as you can see, these transcripts, we merge it with the original data set. And by saying merge, we actually randomly sample from this predicted labels 10% of the data. It's actually hyperparameter. You can tune it further during the training. So we combine this original data set with the predicted data set and put it into the fine-tuning stage. So we fine-tune this model using this newly obtained data, the merged corpus. And we do this iteratively until we reach some good threshold of word error rate. And this technique is called pseudo-labeling, which we just utilize for our use case. And I guess Alexan will take it from here.
Yeah. Thank you. Okay, so these are the methods. Let's get to the results and why actually they matter. So first of all, that we mentioned from the beginning, and we keep it saying, we have fully open source Armenian ASR. It was hard since the dataset are the datasets even available for Armenian, for example, the audiobooks, the YouTube dataset, or just the text corpus that you can ask people to label. Usually they are closed. It's either text like personal contacts with the people to make them open source, or just a very grinding searching of this type of dataset. So first of all, what we get in our results is like fully open Armenian ASR model that's available for both research and commercial use. The second thing is that our architecture and our model is quite small. So it has very high real-time factor, and compared to other like big models, it works very fast, and it's deployable on edge devices, for example. When we released this model, it had state-of-the-art results among the all open models with both punctuation and capitalization and without it. Currently, there are closed models that are better than this. There are also open models that are not available, for example, for commercial use, only for research use, but that are much bigger, much heavier than our model, that have a little bit better results than our. But among the small and open models, we still keep the lead here. And the other thing that we, again, used Armenian language as a case study, and we wanted to make it fully reproducible. So we did also some cost studying. On the right, you can see the table that compares how much data we get, how much man-hour was spent on it, and how much money we spent. So as you can see here, nearly none of the methods actually took money. Only the online crowdsourcing dataset and offline crowdsourcing dataset require some financial investments. Why we have asterisks on the offline crowdsourcing? It's because we just produced some merch and we distributed this merch as a gift for people who participated. Basically, we can do it without any merch, without any just giving out certificates, and that would cost nothing additional. As for online crowdsourcing, unfortunately, there's no way for now to have fully free online crowdsourcing. So people just you need to pay people to work. So this again, the case study on the methods, how they work, and how much investment they need. Okay, so we promised to keep it non-technical, but just a little bit of code in terms of reproduction. Everything here was based on the Nvidia framework. This is fully open source framework named SDP, Speech Data Processor. So manifest is three things you need to take from this slide. So manifest is actually the data file that Nvidia use. It's just a regular JSON-L file with keys. And with keys, usually there is only 3 keys without any additional metadata, so only just text, audio length, and audio path, and the corresponding values. On the left corner, on the left down corner, you can see an example of an entry inside the manifest. The second thing is receipts. So in the SDP, Speech Data Processor, use these receipts to make, as we were saying, like one button data processing. So we have this receipt. It's a YAML file. A lot of receipts are already configured, and just as an example, we even use the receipt that has nothing to do with Armenian. It's a receipt of LibreSpeech dataset. That's English dataset. Just to show you how it works. So it's just pre-configured pipelines that you can just run again with one command and one button, and you'll get results in. You'll get the dataset in the fully processed way, ready for training or testing, depending on what dataset you want to use. Okay, so most of the part, this was our speech. It was me and Ara that presented you the speech, but basically we had a big team working under it. So it was actually Sofa, Maher. Everything was supervised by Nikolai Karpov. Nune was also part of the team, and 2 managers that are not present here. They are US-based, Vitaly and Boris. In the presentation, you can find the links to everything that we talked about, to the toolkit, to the datasets that we released, and to the paper, and etc. Okay, and finally, we just made a small demo. So you can follow the link and test the ISR model that's available now at Hugging Face. So it's just a Telegram bot, just a wrapper. Also, we're happy to hear your questions. Yes.
Thank you, first of all, for the presentation. My question is about the pseudo-label data, because it is a good half of your data set, if I'm not mistaken, the 140, more than 140 hours. So I just want to ask, what are the methods of verification that this data can be used? So are there some measurements of the quality of this data, some statistical or other measurements, so it can be used in for the training? Thank you.
Sure. Thank you for the question. So yeah, it's almost half of our data that we obtained, and we can actually scale YouTube's data infinitely almost, because there are tons of data in YouTube. The methods that we use to validate, first of all, the pseudo-labeling is an iterative training algorithm. So we terminated the training when we get good results in terms of word error rate for our model. But besides, we do, as you said, like statistically how to define. We have this metric, POI. It's the reference is in the. There's a reference for this paper. It's a metric that kind of using bootstrap techniques to give some confidence interval regarding the significance of change when you compare two models. So what are these two models? So we obtained a couple of sources of data, audiobooks and viewers. To test the usefulness of this YouTube data, we conducted two experiments using combination of this data without YouTube data, without the pseudo-label data, and using the whole data, and obtained two models and compare them, both by word error rate, like precise comparison, and using these confidence intervals. Here we can see just the results with the pseudo-labeled data. When we add this on top of whatever we had, we get much better results. This is like 10% improvement over this. But we also, I don't know if we have this on appendix regarding
we don't have the POI, I believe.
I see. So there is the thing called this POI, the confidence intervals. We also saw with, if I'm not mistaken, 90%. The significant level was 90%. So we were 90% sure with this technique that adding this pseudo-label data eventually significantly improved the model performance.
Yeah, thank you for the presentation. I wanted to ask about the pipeline when you did the character matching between the predicted text and the actual transcription. I wanted to ask how you cut off the text, because the first slide you showed, the Telegram model, it predicted the first part wrong and the second part right. And how do you go in both sides and know that this is the right cutoff for this audio?
Sure, thank you for the question. This is the the most challenging part. This block is the most challenging part of this whole pipeline. The algorithm itself, it's a lot of code, but in words you have a long transcript, the original one, and you have small predicted chunks. As we use already more or less a good model, the provided chunks are within 30% word error rate. So what we do, we take this our long transcript and some slicing window. When we slice with this window, we compare to we sequentially order these chunked predicted outputs. And when we're sliding through this original label, we just compare through these predicted chunks. And this original labels window, we actually take a couple of possible chunks because we don't know the actual size matching. We have this, let's say, plus minus size of window lengthening in the algorithm. And when we took these segments, we just compare character error rate and take the based one and continue consequently. And the algorithm works in terms of it's greedy because when we take only the best one at this moment, and it's also dynamic because depending on the nature of the pipeline that is consecutive, if you miss something, let's say one word from this predicted transcripts, this error will propagate to the rest of your algorithm. That's why even small significant error could result in a crash. So we dynamically adjust the window. Maybe we start with this, match, this is the whole text, we match this chunk, we need to go this to the next chunk, but maybe there is an error here, which resulted for you to take an extra word. So for the next chunk, we don't take immediately thereafter. We can also have some overlaps to cope with this error mitigation, error propagation. And I can provide the test that how we tested this algorithm. An easy case is the following. You have this MCV data, which is labeled. It has like 50 seconds long audios. So what I did, I combined all the audios, like these 50-second audios, and obtained 60 hours, or I don't remember how much, long of one long audio. And also combined all the texts. So from this MCV, I get the full transcript and this full text. And as a replication of this pipeline, the original, this original small 50-second audios, they kind of act for me as these chunks. So I don't need to do the VAT because I already had the chunks with the correct labels. And I used the same algorithm for this MCV's original small audios and do the character matching. And eventually, it was not just character error rate match, it was like 99-point-something% accuracy. So by saying character error rate, you can have one long sentence, and within that one long sentence, you can have one letter misspelled. It can have, I don't know, maybe 90-something% character error rate. And for accuracy, you need an exact match. So out of these all audios, the match was 100% in all cases, almost all cases. That's why the accuracy equaled 99-point-something%. This is not the natural way of testing this pipeline because we skipped this one in my described process, but it was the most available thing to do, and here it is.
And it worked. We know that it worked.
Thank you for, you did a great job. Thank you for representing it to us. I would like to ask one bad question about legal side. You said that you used YouTube audio to train your model. Could you please tell me about the legal side of these things? Can we use just YouTube or some open source video or audio to train our model?
Let me answer maybe this.
I know this is a
No. This is exactly why we have this low amount of YouTube data. So YouTube is big. We could take like the whole Armenian YouTube. 149 hours is actually the amount of data that we were able to find. That is actually fully open source and matches our matches the license that we open sourced our model with. So yeah, coming to your question, it's from legal side, we did a great job here. That everyone from the team to make sure we don't meet any like legal constraints. Also, one thing here is that, for example, for YouTube dataset, we are not allowed to publish the dataset itself. So we just publish the IDs of the videos that we used, because again, to some constraints of the YouTube, we just cannot take their audio and like present it as our dataset. So yeah, for that we just produce the IDs and also give the tools to download this exact audios and prepare it to the matching format.
Thank you for the talk. I have a question regarding speech data processing pipeline. Is it possible to set up, I have two questions really. Is it possible to set up not linear pipeline, but a directed acyclic graph? And is it possible to set up it via graphical interface and not via markup language?
Well, let's start with the markup language. Actually, the receipts, they are just YAML files. We have a lot of receipts there. For speech dataset, like most of the popular datasets that you can imagine, especially for English, it's available. So you just need to run one command and you'll get them. You don't need to implement it from the scratch. When you do, no, only the receipts format is supported by the SDB, so there's no graphical interface for this. And what was the first part of the question? I didn't get that. Regarding the graphs? Sorry?
Can we have not linear path, but a path, a processing pipeline that contains some parallel paths, like a directed acyclic graph?
No, no.
Only linear.
It's mostly linear. It actually depends on the implementation of the processors, but it's mostly linear, and each processor runs it and then goes to the next one.
So it's not possible to set up something that can be made in Airflow.
Okay, let me show. So this is like more complex version of the pipeline that I showed. As you can see here, we have actually two. They are shown as parallel, but they still are linear. So you can implement it to not work on the same dataset. So it doesn't give any constraints that you take one input file and then it always does with this input file. Even though it supports, like, for ease of life, you don't need to pass the input file each time. It will take the output file of the previous processor and then pass it to the next one. But for each processor, you could just take and give at any point give custom input file or other input file, and then you'll get this parallel. If you'll get parallel logic that doesn't work in parallel, kind of.
Okay, thank you.
Just a side note about that, so the processors themselves are built in a way that they act parallelly, like they process parallelly within their scope of the job. So let's say one of the processors needs to handle the silences. You have a large corpus of audios, it will do it parallelly. But you cannot use processors parallelly comparing to themselves. One processor within itself is parallel, but to your question, you cannot create like a different kind of, let's say, parallel jobs. Though you can create some custom form of graphs when you can specify during this linear, let's say, YAML, that after some point you can have a different input for a specific processor, not like an output is the input for the next one, you can specify do some customization. And regarding the Airflow, actually, why would you need to use this within the Airflow? Because it's like a single task. In the scope of your Airflow, you will just run one script and it will divide this one script job into multiple processors. And Airflow would be more useful to use if you had use cases of multiple such pipelines to run, not to divide this within the Airflow.
Thank you. I was just wondering if you have any concrete perspectives of your project evolution. Do you intend to have new variants, Armenian variants, or I don't know, maybe to add different types of data, more naturalistic data, and to test your model?
Okay. So personally, I stopped working on this project from. Yeah, please, our supervisor.
Thank you for the question. We are thinking to use translation, like to implement translation model. So again, we don't have like open source data for translation, but we are thinking to create it using crowdsource or whatever, and create like open text-to-text translation or speech-to-text translation. Yes, this is kind of what we are thinking about.